sketch, appropriate label, appropriate annotation. Which means we gotta get this on our screen. Okay. So brief sketch. Okay, good. Make a quick sketch. Literally, the first sketch is connecting the dots, folks. We're just back in grade school. Okay, so sketch for right triangle. This table up on the board. This table, equation for Pythagorean theorem. Okay, up on the board.
Oh.
This table. This table, equation for that circle. Okay. This table, sketch for a cylinder. Okay, with the radius and the height. So a cylinder. Okay, except for the slant height thing. This table, I want you to tell me the equation for the volume of a cylinder. Put it on the board up front.
Those thing on the. Yeah, that thing. You gotta press it like you mean it.
I mean it.
There you go.
Super. And annotate that circle. Where's my radius? Super. Wow. You just did something for the other table that was really nice. Okay, just a quick glitch here. Scribble out this because cylinders don't have slant heights. For those of us who are looking at that going, huh? And add the slant height to here. Slant height cursive L. Okay, so where's my cylinder sketching crowd and my cylinder volume crowd and volume for a cone? Yeah. So get those up there, the other three tables. Okay.
Well, I wasn't going to, but yeah.
Positive. So divided by the quantity 1 divided by the quantity 2 times 1.7647.
My dad's done that before. Would not take this cold. So awesome. Multiple times. Actually, I don't know. I remember, did I start about 7th grade when
All right, where are my cylinder people? Who has to draw my cylinder? Let's go. Come on. And both the equations. Who are my equations for cylinders and cones? Let's go. No, but thank you. Okay, come on. Who's my cylinder group? Right? Someone's got to draw it. Who's my cylinder equation group? Someone's got to put the cylinder equation up there. Yay, slant height. Thank you, cone group. So remember the slant height on the cone is up its side, L, and there's a Pythagorean triangle inside that cone. People, who are my cylinders? Are you my cylinders? Is R up there? Are you my cylinder equations? Yes, no? Volume of a cylinder? Let's go, come on. Everybody's touching their noses, which is super awesome. We're not gonna play touching the nose anymore, we're gonna play touch your neighbor's nose. It's more challenging. I'm gonna actually give you guys time to work, so we gotta do the class activities fast. Awesome. Please. Okay, getting you to draw pictures, kind of like pulling teeth at this point. You really need them. It helps a lot for these problems to have a picture. Okay? Helps a lot. Kind of like yesterday, I kept drawing, right, the graphs and the tangent lines, and then coloring in the gaps. Okay, so we need those pictures. Okay, what is the volume of our cylinder? How do we find the volume of a cylinder? Pi r squared times height. Okay. Okay, cone, yeah. This divided by 3, right? So if you remember back to geometry, hopefully you had a teacher that brought in a cone and brought in the cylinder and said, here, fill the cone up with water and take that and fill up the cylinder, and they realized that it took three of them to fill up a cylinder. Okay? That's what I do in geometry. I play with water a lot, especially in the volume unit. Okay? Now, how many different variables are in those two equations? I mean, let's take the cylinder equation. How many different variables do we have? Don't say 2. We got 3, don't we? We got a V and an R and an H. How many variables here? If we take the cylinder and start filling it up with water, is the volume changing? Is the amount of water changing in the cylinder? Yes. Is the radius changing? No, that's constant. Is the height changing of the water? Yeah. Okay, so in cylinder type problems, if we think about filling, and related rates have to do with like filling and emptying or movement of a car or something like that. So as we're filling or emptying, we have the things that are changing are volume and height, right? We're always going to have this cylinder of water that has the same radius. How about a cone? As we're filling or emptying a cone, And maybe, you know, if we're gonna fill and empty this thing, maybe if we're gonna fill and empty this thing, maybe we want to draw it like this. In fact, I saw some of you drawing it like this, right? Kind of like those little paper cups that you use at the water things. As we're filling this, let's pretend that's water there. Is the volume of water changing as we fill that up?
Yeah.
So we've got changing volume. What about the height? Is the height of that cone of water changing?
Yeah.
What about the radius? Is the radius of that cone of water changing?
Yeah.
Since we have tapered sides, right? A little bit of water gets us this little radius of water down there at the bottom of the cup. And then as we fill it up, that top surface gets to be a bigger and bigger circle. We've got three things changing there. Okay? So when we start to take derivatives, because rates are derivatives, right? The idea of talking about a rate of change and talking about a derivative is talking about the same thing. As we take derivatives here, we have to take derivatives implicitly sometimes, especially for cones, because we have two things changing here. Sometimes we can draw a relationship. In fact, we're going to do this with one of the examples. We're going to draw a relationship between radius and height so that we can narrow it down to one variable. Okay, that works really nice then. Okay, so any questions about that? When we talk about, I had you do a Pythagorean theorem thing here. There we go. When we talk about A, B, and C, what are A, B, and C? On this picture, if I had to annotate A, B, and C on this picture, I would draw them where?
Based on I guess either side. The bottom.
Okay, yeah, A is one of the legs. What about B?
Leg.
Another leg, and then C has got to be a hypotenuse, okay? So just a note there. Here's the equation for a circle. What is the other equation that we know that we can use with circles?
2 pi r.
Okay. What is 2 pi r?
The volume.
A circle is a flat object, two-dimensional, doesn't have a volume. Circumference. Any other circle equations that you know? Area is pi r squared. Okay, so those are other two things relating to circles that we will end up using as well. The nice thing is that when we're dealing with two-dimensional objects, we only have one variable over on the right-hand side. So the nice thing there is that the derivatives become pretty straightforward. Okay? So just a quick little exercise here. When we talk about a rate, rate has the implication, of being with respect to what? Time. Okay, so did you see the variable t in any of those equations? Nope. So when we take the derivative of any of those equations, we're taking it with respect to an independent variable, which means we need to do implicit differentiation on every variable. So let's try this with area of a circle. We're going to take the derivative of the area of the circle with respect to time. Okay? And I'm going to have you use the Leibniz notation, the fraction notation, the dy dx, or in this case, the d something dt. Okay? Is pi a variable? Nope. Okay, good. All right, so what's this derivative? Okay, really close. Pi times 2r, and I realized people were saying 2 pi r. That's the same. You took the derivative of what variable? R, right? 2 pi r. But we have to take that 2r is the derivative of r with respect to what variable? No. In other words, if I have x squared and I say the derivative is 2x, I've taken the derivative of x squared with respect to x, right? I've just done the power rule. So if I take my r squared and I say the derivative is 2r, I've taken the derivative of r squared with respect to r. I need to take it with respect to t. So what do I need out here? R prime, right? Our implicit differentiation. And that equals what? A prime, right? I took the derivative. It's got to equal the derivative of the area. Now, I think that for related rates, for implicit differentiation, I know we use the primes a lot. For related rates, I would like to use the Leibniz notation. So this becomes dA d what? dA dt, because we're taking, I want you to acknowledge that the variable that we're differentiating with respect is time. Okay, so we can get that rate. Okay, so this is the rate of change of what? Area with respect to time. Okay, so we're seeing how big that circle is getting, or small that circle is getting, growing with respect to a second or a minute or an hour. Okay, and then I'm going to say it, I'm going to write this like you said it earlier, 2 pi r, and then I'm going to have you write the Leibniz notation there, dr dt. Okay, so differentiating area looks like that. Okay, and then we can talk about how fast is the circle getting bigger or smaller? What's the rate of change of the circle? How fast is that radius getting bigger or smaller? Does that make sense? Okay. At a specific point in time, when the radius is a foot, how fast is that radius growing? When the radius is 6 inches, how fast is that radius growing? Okay, so those are the types of questions we're going to work on. Let's take a look at, I want to take a look at the volume of a cone first. Because what did we say about the volume of a cone, about the radius?
It's a third of it.
Well, I don't know why I said cone. A volume of a cylinder. What do we know about the radius of the cylinder?
Doesn't change.
It doesn't change. So when we take derivatives, that is a constant. Okay? When we take derivatives, the radius is a constant. That radius is the same no matter how filled up that cylinder is. But the height does change. So here is our variable. And here is our variable, our changing quantities. So when we do the implicit differentiation here, those are the quantities that are going to have derivatives associated with them. So what's the derivative of v with respect to time?
dV dt.
dv dt, exactly. The left-hand side is usually ends up just being a simple Leibniz notation. Okay? All of the constants can be just written down, unchanged. So what am I going to write down next on the right-hand side here? Pi r squared. And then what's the derivative of h?
H prime.
H prime. So I'm going to write that dh dt. Make sense? Doing okay so far?
You don't change the pi square because it's a constant.
Yeah, because we're talking about a cylinder. Yeah, so, you know, as we're filling up that cylinder of water, or if that cylinder is full and we poke a hole in the bottom and let it drain out, okay, as that water level is changing its location, that radius isn't, it's always the same. Or we could say its rate of change is 0. We could also look at it that way. And so this simplifies things, because two variables here multiplied together, typically we would have had to do a product rule on. But in the case of the cylinder, we don't have to, because we know one of them doesn't change. In the case of a cone, and there's a reason why I'm going through the derivatives of each one of these, is because these all show up on your WebAssign. If we look at the cone, and we look at filling up this cone here, as we fill that up with water, is this height changing? Is the level of that water changing?
Yeah.
Is the radius of that water changing? Yeah. So if we look at the volume of our water here, 1/3 area of the flat surface or area of the base of the water times the height of the water, this is now changing, so this is now variable, and this is changing, and this is changing. Okay, and when I use the term variable, I mean it's changing. It also happens to be a letter. Hence the reason why we call letters variables. Okay? And if we don't know a relationship between R and H, we're going to have to use a product rule here. Yeah. We're going to have to use a product rule here to find the derivative. Okay? I'm going to take you through the product rule on this one, but then the example we're going to do in class on the next slide or two is there's actually going to be a relationship between these two, so we can eliminate one of the variables, and then the derivative is much easier. Amanda, you had a question?
All right.
Okay, you sure?
Yeah.
Okay, give me a holler. You need to answer. Okay, so let's go through the product rule here. Derivative of the left-hand side is what?
dv dt.
Just the rate of change of volume. What are my constants here?
1/3.
Okay, so my constants are the 1/3 and the pi, and now I have to do a product rule. Okay? So let's take the derivative of r squared. What's the derivative of r squared with respect to t?
2r prime
2r prime, right?
and then h.
So 2r times r prime dr dt. So there's the derivative of r squared. And then I have to multiply that times the other variable h. Right? So derivative of the first times the second plus
Squared plus dh.
the first times the derivative of the second. What's the derivative of h?
dh dt.
Right, that's like saying what's the derivative of x, and that's just 1. But since it's implicit, it's 1 times dh dt. So there's the derivative when both r and h are changing, and we can't find a relationship between the two. Okay? How are we doing? So if we look at this as r squared h, okay, two variables. This is the derivative of r squared, and then this is times the other one, the product rule.
Oh.
So we're looking at kind of like f of x times g of x. You know, so we take the derivative of f of x times g of x plus f of x times the derivative of g of x. Does that help? Okay. The nice thing is, I just wanted to throw this out there. This very rarely happens. Okay, it won't happen on the WebAssign. I'm digging through AP questions. I haven't found anything like this. It's a possibility, but I haven't found it yet. Okay. The next card is basically going through the related rates problems. Get a sketch, get an equation, and identify where your variables and constants are, and then we got to set up and solve it, which is really, after you take the derivatives, all algebra. But around the whole steps and everything are all of the equations for volumes and surface areas that you learned in geometry. Amanda?
I was just wondering if we were actually gonna, like, with the next problem, if we were gonna learn how to calculate time. Like, are we gonna find time, or are we just doing that?
Are we going to actually work through a problem?
Yeah.
Yeah, we're going to work through two of them. I was just kind of buying a little time here, not to be funny, but can I go to here? Okay. Okay, so here's all our cylinder equations. Here's our Pythagorean theorem. Here's our circle equations, our sphere equations. Okay, all of those things. Okay, so if we are filling up something, what do you suppose about the rate of change in volume? It's going to be positive or negative? Why? Yeah, because you're gaining volume, right? Volume's a positive number. We're having a positive change in it. We're gaining more volume. So we're going to have a positive rate of change. What if we poked a hole in the bottom of the cylinder and let it drain out? Is that going to be a positive or a negative rate of change? Negative. Okay? So in other words, we have this volume and we're taking it away. Taking it away is a subtraction sort of process. So if you look at the kind of the asterisk down here, distances and lengths are always positive. Radius will always be positive. Height will always be positive. Okay, but the rates will either be positive or negative depending upon if they're adding to the variable or subtracting from the variable, the quantity. Okay, so let's try this one. And for this one, I just included the sketch for you. We've got a squad. It's approaching an intersection. So here's our squad. It's approaching an intersection. And it notices a car speeding over here. And that car has turned the corner and heading east. And it says that we know the squad is going 60 miles per hour. And we know the distance between the squad and the car is increasing at a rate of 20 miles per hour. What does that mean? Where is that represented on this picture? Who said, what did you say? Hypotenuse, exactly. The distance between the squad and the car. Whenever they say the distance between two things, they are always assuming it's a straight line distance. So the distance between the squad and the car is this location here. So the squad is driving, they're pointing a radar gun at the car, and they're seeing the reading on the radar gun changing 20 miles per hour. Okay? So they're seeing it, this is oversimplifying it, but just as an example, they're seeing it go from 40 to 60 to 80. Okay? But they're also not traveling in line with it, so it's a little deceptive as to what that really means. So if you notice then, we're talking about this distance, which somebody says a hypotenuse, so what would be a reasonable variable to put on the picture right here? C, exactly. And so if we talk about then this distance of the squad and the distance of the car here, that's going to be my what's?
Like, geez.
your legs A and your legs B. Okay, so there's our sketch. How am I going to relate, we call this section related rates for a reason. How am I going to relate those three quantities? What equation am I going to write?
Pythagorean's theorem.
Pythagorean's theorem. So I'm going to go ahead and write c squared equals a squared plus b squared. Okay? And then now you have to kind of envision this actually playing out. So a squad car is moving, the car they're chasing is moving. Is the length A, the length B, the length C changing? What's changing here? Is A changing?
Well, they're all changing.
Is the squad moving? In fact, the dimension of A is getting bigger or smaller? Smaller. Okay. Is B changing?
Yeah.
Is the car moving? And it's a safe bet then, if A is changing and B is changing, is C changing? Probably. Okay. In fact, we know it is because we see that the increasing the rate of distance here is increasing at 20 miles per hour. So at this point, what we know is we have three variables and they're all changing. So let's go ahead and make a little chart here. A equals B equals C equals. At this point in time, at this instance, we've got this information. Okay? So, judging from that information, can anyone tell me at this snapshot how much A is?
0.6.
A is 0.6 miles. I'm running out of space. Does anybody know what B is? 0.8 miles. Does anybody know what C is at this instant?
1 mile.
Okay, Tyler says he knows C is 1 mile. And he's right. And maybe after Tyler said that, people go, oh, now I see why he knows that. Tyler, why do you know that?
6 squared is 36, 8 squared is 64, add them together, it's 1 squared, and 1 is 1.
Yes. Right, he just did Pythagorean's theorem. Okay, so that snapshot, that still photo at that instance, we can do a quick Pythagorean's theorem and find the hypotenuse. Now, we said just a second ago that these are all changing, which means these all have what? They all have a rate associated with them. So what is my dA dt? How much is it?
6 over 6 over 6 or something.
What is the rate of change of my length here? What is it associated with?
Sounds pretty.
It is associated with miles per hour. What object is causing A to change? The squad or the car? So what is the squad's rate?
60 miles per hour.
60 miles per hour. Okay, now is that rate, right, here's our distance of length, our unit of length, here's our unit of time. At that rate, is that rate causing the length A to get bigger or smaller?
Smaller.
Does that make sense? The squad is driving and that 0.6 is getting smaller and smaller and smaller as the squad's approaching the intersection. That distance is decreasing. So that rate then is what? It's negative. Because it's causing that dimension to get smaller and smaller and smaller.
Why do we know?
Well, we know rates have a unit of time in the denominator. Okay? And so we look at what we have here, and it's these two numbers that have a unit of time in the denominator. So these two numbers have to be rates. Yep. Well, you remember the negative sign for physics means direction, right? Which direction is this car traveling? downward, right? We can look at it that way. In all reality, it's negative because this is 0.6, but as this rate is affecting this distance, it's causing the distance to decrease. So this distance is getting smaller and smaller. Yeah, totally. Yeah, exactly. How about the car? Do we know the car's rate, the derivative for B? Do we know dB dt? Is it 20?
No.
Why? Okay, so Tim is saying no, it's not 20. Why is dB dt not 20? Because there's angle. What is the 20 associated with?
How fast is it? How fast are you?
The change of what?
Velocity.
Oh, okay, good, Brad. Brad is saying, wait a minute, this is the distance between them is increasing. What variable is the distance between the car and the squad? It's C. So we know that dC dt has to be the 20 miles per hour. I can write it like that too. I'll change it. Just to be consistent. Okay, and so what's the question of after we get done with all of this, what's the question really? What are we being asked to find? What is dB dt? dB dt is how this distance is changing.
It's the derivative.
So if it's how this distance is changing, then it's related to what object in the picture? The car. Is dB dt a rate?
Yeah.
So it's the what then?
Derivative speed.
It's the rate of the car. Exactly, it's the speed of the car. In other words, it's really what we're being asked to find. Does that make sense? Because we're being asked to find what the speed of the car is. So here is our unknown. So when we take the derivative here, we're going to have to take the derivative with respect to all three variables. So we have c squared equals a squared plus b squared. Okay, this is the situation where the left-hand side is going to have a chain rule in it. So what's the derivative of c squared with respect to t? Yep. Exactly, 2c dc dt. What's the derivative of a squared? Same thing except for a, right? It's 2a dA dt. What's the derivative of b squared? 2b, right? Just the power rule. But then we're taking the derivative with respect to time. That's that independent variable, so we need to use that implicit expression, that chain rule, so to speak. Okay, so we have to solve for, sorry, I tried to scroll up, but we need these numbers. There we go. Is that good enough for now? How much is C?
20.
Disagree. How much is the variable C? Okay, so 2 times 1. How much is the rate of change of C with dc dt? 20, yep. How much is A? It's 0.6. Okay, how much is dA dt? Negative 60, because it's causing that 0.6 to get smaller and smaller. How much is B? 0.8. How much is dB dt? That's our unknown, yeah. Okay. All right, and then we crank and math and etc., right? So this ends up being 40. This ends up being something. Let's see, this is 1.2. You would get a calculator for these sort of
Negative
numbers.
72.
Thank you. It's a little much for me. And this ends up being 1.6 dB dt. Okay. So a quick little algebra maneuver here. And we end up with an answer of 70. Now this is, in these problems, units become really important. This is the rate of change of length b. So what is the appropriate units here? Miles per hour, exactly. And if the units are getting you a little messed up, go back to the question and say, what am I being asked to find? Oh, speed. Right? What is my speedometer reading? Grab the appropriate units. Does it make sense that it's positive? And because, you know, the car, the length b, where the car is traveling, is getting bigger and bigger, right? The car is getting farther and farther away from the intersection. Okay. How are we doing? You could use the primes. I'm using the you remember the top bottom expression is called Leibniz notation. I'm using that just to reinforce that it's a rate of change with respect to time. Okay, it helps with the units sometimes.
What does it mean that we become with respect to time?
In other words, my distance, my mileage is changing with respect to some sort of unit of time. Seconds, minutes, hours. In this problem, it's hours. Does that make sense?
Yeah, so will we ever get solved for T or anything in this problem?
Nope. You'll either solve for a distance or a rate. Okay. Two other applications of Pythagorean's theorem in where it gets to taking the derivative of Pythagorean's theorem is a little more simple. So if we look at this scenario here, we've got an airplane flying at a constant altitude. So this, we'll call this variable, let's just call this variable A. So A is always going to be 7 miles per hour. So as this airplane flies horizontally, this horizontal distance x is getting bigger. And the hypotenuse s is also getting bigger. So the rates of change are going to be positive because it's increasing the length of those two things. But the A is always going to be 7 miles per hour. So as we write the Pythagorean's theorem here using these variables, we'll have a leg squared plus a leg squared equals the hypotenuse squared. And since the x and the s are quantities that are changing, when we take the derivative, we'll have a differential there, the dx over dt and ds over dt. But this is just a constant. So really, this is literally 7 squared. This is literally 49. So when we take the derivative here, this is going to be 0 plus 2x times dx dt equals 2s times ds dt for the expression of that derivative. So it is literally like you could literally put in 7 for A. You could really write this this Pythagorean's theorem as 49 plus x squared equals s squared. There we go. Equals s squared. And then, you know, taking the derivative of 49 gets you 0. So here's the expression of that derivative right there for that Pythagorean relationship. Like in similar fashion, if we look at this one here, we've got a ladder, and this ladder is sliding. It's, you know, it's like on a slippery floor, so that the bottom is sliding out. So the bottom of the ladder is moving in that direction, which is increasing this distance. We can call this distance b. And so since this motion is causing b to increase, it's going to have a positive rate of change because b is getting bigger. So this is getting bigger. And so, and since the top of the ladder is sliding down the side of the building or the wall, this value is decreasing, so this is getting smaller. So this rate of change will be negative. So maybe we'll call this A again. And this ladder is not changing size at all. It's just the same length all the time. So this means that the hypotenuse is not changing at all. So that's staying fixed at 13 feet. So if we write the Pythagorean's relationship again, and take the derivative here, we can literally really rewrite this as a squared plus b squared equals 13 squared. A squared plus b squared equals 169. And we can literally take the derivative of that. So this is going to be 2a times dA dt plus 2b times dB dt equals derivative of 169 is 0. So here's that derivative expression for that relationship of that ladder sliding down the wall. All right, let's take a look at water filling up a tank. What is the shape of the tank? It's a cone. Yeah, conical means cone. Okay, so we're filling up. Cylindrical would be cylinder. Yeah. So we're filling up a tank. We're going to draw the tank like this. Assume we're filling it up from the top. Okay. And anytime we fill up into anytime we're filling things, we're talking about what? Yeah, we're talking about volume. So we know that we have that relationship between volume and the variables that we would associate with the water level in this tank. So here's the water level. We know that, as we're filling it up, this level is changing, right? So if we take a quick snapshot of that, we have a height and we have a radius at a given instant in time. Okay, and yeah, when we take that snapshot, we have a height equal to 6 feet. Does it say anything about the radius?
No.
No, it doesn't. But then it gives you the shape of the tank. The overall height of the tank is how much? So the overall height of the tank is 10 feet. So when the tank is full, the red H is going to be at 10 feet. Does that make sense? Okay. And the overall, what else do they give? They give the radius of the tank?
Yeah.
Okay. So the overall radius of the tank is how much?
5 feet.
It's 5 feet. Okay. And we could do the really messy derivative like we did on the first page of this. But since they've given us a relationship between the height and the radius, in other words, the height is twice the radius, we can get a relationship between H and R. And if we can get a relationship between H and R, then we can use that relationship to get rid of a variable. And that really helps. Does that make sense? So we're going to write a ratio here. We're going to take the tank. We're going to write a ratio of R over H. So 5 feet over 10 feet. And then we're going to write a ratio of the water. So what's my variable for the radius of the water? Red R. What's my variable for the height of the water?
6 feet.
Okay, yeah, I'm going to leave it as H right now. Okay, and Tyler's saying 6 feet. So let's just do this intuitively. When my height is 6 feet, how much is my radius? Does anybody know? If the proportions are all the same? when this is 10, this is 5. If this is 6, this is going to be 3. Okay. Let me just give you kind of a visual picture. So we know it's a 2-to-1 ratio. Okay. So let's see here. Which one would be easier to substitute variable or an expression in for? R squared or H?
H.
Yeah. Let's solve this for H. How much is H? H is 2R, right? Now, so if we take a look at what we have here, we've got a height of 10 and a radius of 5. That's the tank. We've got a height. We've got a, at this instant here, at that instant, do we know the height or the radius? We know the height. What that means is that since we have information about the height, and we want to know, what's this? How fast is the water level rising? What is that? It is a rate, right? Because we're saying how fast. So we know it's a rate. The rate of change of what? The height. So we know this is a dH dt. So when we look at that volume equation, we better have that volume equation in terms of what variable? H. Because we have information about that, which means we got to get rid of what? The radius. Exactly. We gotta get rid of this radius. So let's take this expression then and solve it for R. So we can substitute that radius out. So what do we have here? Right? We just multiply by H, right? So we have 1/2 H equals R. Right? The radius is half the height. Radius is half the height. You said that was 3. Radius is half the height. So we're going to put that in for the radius. So our volume expression now becomes what? And I got to square that, right? Because this is my radius. I need a radius squared. When I square that, what do I have? Okay, let's simplify our constants. Okay, when you simplify our constants, what do we have? Yeah, we got, I'm going to call it pi over 12, h cubed. A little simplifying goes a long way because that's not that bad of a derivative to do. So now we're going to take the derivative with respect to time. Okay, so now what we're really looking at is we've got a variable v, and so we know we're going to need a dv dt, and we've got a variable h, and we know then we're going to have a rate dh dt. Okay, so what's the derivative of v? Okay, I agree. You got some components there that we need. What's our derivative of the variable v? dv dt. I know, it's deceptively simple. Okay, and then pi over 12 is a constant. Now what's the derivative of h cubed? 3h squared dh dt. Exactly. Always looking for that rate because we know it's it's a rate of change with respect to time. Okay, so now our snapshot. So we're going to go back up to that red picture for our snapshot. Do we know our volume at that point? Okay. So going back up to this information here, okay. Do we know our volume at that point? No, we don't. Okay, do we know our rate, how our volume is changing? How much is it changing by? 9 feet cubed per minute. Do we know our height at that snapshot?
Yeah, 6 feet.
It's 6 feet. Do we know our rate of change of our height, how our height is changing?
No, that's what
No. What was that comment, Amanda?
we have to find it.
We have to find it. Yeah, that's what we're being asked to find. Does it matter? Those are question marks. Does it matter that we don't know the volume? Yeah, why doesn't it matter that we don't know the volume? It's not in the derivative. Yeah, exactly. Right? And so we don't really care. Don't know, don't care. It's one of those nice ones. Okay, so how much is my dVdt? 9. We got pi over, we really have pi over what number?
4.
Pi over 4, right? 3 on the top, 12 on the bottom. How much is our h?
Wait, 6 squared.
Yeah, 6 squared dH dt. So how much is our rate of change of height? Would anyone believe that? Yeah. What are the units? Okay, so let's look at this because they will literally give you points for correct units, almost like a physics exam. For these type of problems, what's h measured in? Feet. Right. This is why the Leibniz notation is so helpful with the units. We know h is measured in feet, so we know we need feet on top. What's t measured in? So we know we need minutes on the bottom. Okay, if that were a v, it would be feet cubed. So that's why the Leibniz notation is really useful for that last point that you get when you get the units correct. Okay. How are we doing? Okay. At this point, we're basically done. So when we see each other tomorrow is literally just a work day. You're gonna come in and crank it out. Okay? And some of you really, really need it. Big time.
That's true.
Okay? Yeah, let's get crack-a-lackin', definitely. Okay? Where can you find help? What can you do? You've got the video, right? The notebook videos. You've got the lecture videos. Notebook videos, lecture videos are both on Blackboard. Okay? That's how you can get at them. You can also, in your moment of desperation, shoot me an email and I can point you in the right direction. Okay?
I'm like, okay. Good.
1 divided by pi is 9 divided by 20. Thank you. I don't understand.
Instead of just leaving it as pi, I multiplied it all out.
Okay.
Because I calculated.